Sure, can start.
Okay. So hi everyone. This is Mayur along with Vedang, and today we'll be presenting paper number 10. Now, before I start, I will be honest with you. This paper, I found it to be a bit different from all the other papers that we have seen so far, because of the fact that, this paper does not invent or discover anything new. What this paper essentially is doing is it's proving that there is this system which was built by someone else, and this paper is secure enough, this system is secure enough to be used in highly critical security applications. So this is what this paper is all about. And if you look at the title of the paper, it makes no sense, at least to me. But if you're on the same page, don't worry, I'll break it down for you. So let us go to the introduction section. Next, please. So what this paper presenting is basically the first formal verification of information flow security for a general purpose microkernel, which is SEL4. I know a lot of keywords over there. Don't worry, we'll explain all of these keywords as we go through the slides. So what's unique about this paper is that this proof it actually applies to the actual C code implementation of SEL4. All the other previous security proofs for OS kernels, all right, they apply to an abstract model and not the actual code. But this paper, it actually applies to the actual C code implementation, which itself is a very big accomplishment. And this paper basically demonstrates that a microkernel like SEL4, it can be mathematically proven to enforce strict isolation between components. What do I mean by that? That means that there is no data leakage between these components. I'll talk about what these components actually are later on the slides, allowing it to be act as a separation kernel. Now, what is a separation kernel? We'll discuss about it later in the slides. Next, please. So what makes this paper so significant? Like already said, it's first of its kind. This is first of all a formal verification. So there is no test case generation. It mathematically proves that this kernel, it enforces secure information flow security, and it applies to the actual C code implementation. And this SEL4 microkernel is available commercially. And so let's say you're some military guy, and your team is planning to implement a system, right, a very secure system, and you're looking for a kernel, right? So you can read this paper, and then by reading this paper you will know that okay, SEL4 is secure enough, and you can use it in your application. So yeah, that's why this paper is so significant. If we go next, before we go any deeper, let us just briefly understand what a kernel is. Now already I am sure that most of you already know what a kernel is, but I'll just give you a brief overview of what it actually is. So kernel is nothing but a bridge between software applications and the hardware and system resources. So let's say there is an application on your PC, let's say MS Word or anything, and that application wants to read a file or read some data from a memory location, right? Now it cannot directly do that because it doesn't have an access to the memory directly. It has to ask the kernel to do it for them. So it's going to ask the kernel, hey, I want to read from this memory location. Then the kernel is going to check if the request is valid or if the application is authorized to do so. If yes, the kernel is going to do it for it, and then it's going to send the required information back to the application. So and so the kernel is a very important part, in fact one of the most important components of the operating system. It does many other things like scheduling. It tells the CPU what to do, when to do, and many other things. So that's what a kernel is essentially. Now, what's a kernel? So in this paper, the kernel that we'll be having is a microkernel. Now, kernels are of two types. There is monolithic kernels and there is microkernel. The kernels that we use in our PCs, that is monolithic kernel, and in monolithic kernel, all the OS services, they run in the kernel space. But in a microkernel, only the most essential low level functions, they run in the kernel space. Let's say that is IPC, CPU scheduling, and memory management. all other OS services like device drivers and networking, they run in the user space. So if these services want to access the memory, they need to make systems call and all. Now, why do we need microkernel? So obviously, because only the most essential services are in the kernel space, there might be some impact on the performance with respect to a monolithic kernel. But this design of microkernel, it makes it, much more secure and reliable. And let's say if someday one of the services in the OS services in the user space it crashes, then the entire system does not crash. But in monolithic, if let's say any of the OS services crashes, it will crash the entire system and you will get a blue screen. So yeah, so this paper is implementing, or this paper is all about a microkernel. So let us go next. So SEL4 is a microkernel, high performance microkernel, and the services that it includes in its kernel space are threads, capability management, virtual address mapping, IPC communication, and interrupt delivery. Now, most of you would already know what are threads, virtual addressing, and all, but you would have heard of capability management, and that's because capability management is a feature of SEL4, and I'll talk about what these capabilities actually mean. So if you see right in front of you, capabilities are nothing but security tokens that give permission to access specific resources. I'll get back into what those this really means. Other than that, SCLE-L4, it has a small computing base and it runs on ARM processor. So now let us talk about capabilities. So just like kernels are a core component of OS, the capabilities are core component of the SEL4 microkernel, and it sort of forms the foundation of security and resource management. See, SEL4 as a microkernel is quite secure, and it's because of capabilities. Now, capabilities are very secure tokens that grant access to specific kernel objects and define what sort of permissions operations are permitted on these kernel objects. Now, what are kernel objects? Now, these are basically data structures that represent system resources and services, such as threads, processes, memory management, and all. All of these are kernel objects. So capabilities specify, which operations can be performed on a particular kernel object. And now let's say that there are 2, 3 kernel objects, right? So capabilities define, if kernel object 1 can communicate with kernel object 2, and if so, what level of communication. So through capabilities, this SEL4 enables fine access control. Now, let me give you a very simple example of a capability. So, like I told you, imagine capabilities as security batches. All right. So, if there is a thread with read-only batch, it means it can only to a particular file. It means that it can only read that file. If another thread has full access batch to that same file, it means that it can read, write, and delete those that file. And so that's what capabilities are. And no thread, or no kernel object can upgrade its permission, upgrade its capabilities. It is already pre-assigned and it is all managed by the kernel. Can we go next? So now let's talk about information flow security. So the name itself, tells a lot about what this actually means. Now, information flow security is a very broad term, and there are many policies within information flow security. Now, this paper focuses on a very specific information flow security policy about which we'll be talking later on. But in general, information flow security says that information cannot leak from high security components to low security components in any way. And so I've given a small example code in front of you. Now, this code is very trivial. Like no one's going to write this code, obviously, but this is just so that we can understand, what information flow security violation means, all right? So in this example, you can see that the public variable, it depends directly on the secret password. So this basically creates a side channel where the secret information, it leaks into a publicly observable variable. So if there is an attacker that can who can observe this public variable, he can observe this public variable, and infer whether secret password is 12345 6 or not. So that's what information for security is, in general. Can we go next? So now, like I already said, that SEL4 is a microkernel, and it offers good security. It offers good security level, but it's not secure enough to be used in highly critical systems like avionics or military. Um, that's obviously because this was not designed to be used as a strict isolation providing kernel, all right? So although it has features like capabilities, all right, it does not inherently enforce isolation between components. So what I mean by that is, in SEL4 microkernel, there will be many processes, and there can still be data leakage within these processes or partitions. So we cannot use it in highly critical systems. But turns out that this SCLL4 can be configured to act as a separation kernel. Now, what is a separation kernel? So a separation kernel is a type of a kernel that divides the OS into partitions. And these partitions are basically isolated environments and that do not depend on anything else. So these partitions, they can run on its own. So this separation kernel is an ideal kernel that is used in high level security applications like avionics and military. And this SCL4, by configuring by making a certain changes to its configuration, it can act as a separation kernel. So what this paper is essentially doing is, at first it is converting this SCL4 microkernel from into a separation kernel, and then they are implementing their formal verification. Now we'll talk about what these changes were in the next few slides. So SCLL4 already has strong access control mechanisms, but it lacked formal guarantees that information flows between partitions. So by configuring SCLL4 as a separation kernel, we enforce mandatory information flow between partitions while maintaining its general purpose capabilities functionality within partitions. Now I'm using the word partition a lot, so let me just explain you what a partition is. So in a separation kernel, partition is an isolated environment when an entire application or process run independently. So it can so a partition can handle an OS itself. So it's so independent. So let's say there is like a system where there are multiple partitions, right? So the partitions, they run as if they are the only partition in the current system. And partitions can communicate with each other definitely, but that is only through explicitly allowed channels. So separation kernels, they have partitions, and separation kernel, they enforce strict isolation between partitions in a way that these partitions can only communicate through authorized channels. So that is what a partition is about. And partition contains like threads, kernel objects. It has its own memory space and virtual address mapping and all. So just like the process, but it is much more isolated. So, and let me give you an example of where a separation kernel can be used. So imagine that in an airplane, there are many subsystems, right? So there is a flight control system and there is an entertainment system, right? Now and obviously this airplane will use a kernel, right? So using a separation kernel, it ensures that information from the flight control system never leaks into the passenger entertainment system. So in this way, let's say if some hacker gets access to the passenger entertainment system, he or she still cannot access the flight control system. And let's say for some reason the passenger entertainment system crashes, that it won't affect the flight control system in any way. So that is the application of separation kernel, and that is why it is so essential to have a very secure separation kernel. So next, Vedang will be taking over.
Okay, thanks, Mayur. So now that we know the use case of the SEL4 microkernel, we can take a look at how it was actually implemented and what kind of constraints were put into place for it to be this secure. So, as Mayur explained, We might have different partitions in a microkernel, which are basically different parts of the same system, as he explained. Let's say it is part of a plane system, aeroplane system. One is a passenger system, one is the flight control. So we need to make sure there is no data leakage between these two partitions. So to create this, um, what SEL4 does is it enforces like strict time isolation between partitions. Like instead of using dynamic scheduler to run which partition will be actually be implemented, a static round robin scheduler is used. Um, this allows each partition to have some fixed time slice, and that too in a fixed order. So everything is certain instead of being uncertain, which can lead to security issues. Um, the second part, like the three, like these are the three main components of the implementation. The second part of the implementation is capability confinement. So as explained earlier, capabilities are basically access restrictions, like which resource will be able to do what. So the kernel enforces that the capabilities which are created within a partition always stay within that partition. This allows that in no way a thread in one partition can access the capabilities in another partition, um, intentionally or even accidentally. The third part is controlled communication. Like each, uh, the communication between two partitions is allowed only in specific scenarios, like through shared memory or through an asynchronous endpoint, which is like only one way and it does not support replies. More importantly, like synchronous communication between two partitions is not at all allowed. This is to avoid any covert channels which can arise out of replies or just the communication between two partitions. Um, so how this was created was this team had already initially built some type of functional correctness and like the integrity enforcement. They had done some proofs to create this. The C implementation of uh, the CL4, it's supposed to work exactly at it as it is. So they had used an Isabel HOL machine checker to implement, like to verify this. Also, the integrity enforcement was done um, through creating a formal model of this microkernel. In the next slide, we'll see how this formal model was created and how eventually how it was verified. Right. So to create a formal model, the team, like the authors, use some type of it's a intransitive non-interference. Uh, Basically, it is the non-leakage of information within partitions. Um, so, like non-interference at its core means that like a high security domain or like a high security user cannot affect what a low security user observes. So uh, essentially what it means is like A can send data to B, B can send data to C, but essentially A cannot send data to C directly unless it is allowed by the information flow policy of this system. So the authors used information flow tracking kind of principles to actually implement this uh, in the formal security checker, right? So now we'll see how this information flow was actually controlled. Um, so as I mentioned earlier, the like no domain can observe like differences in system uh, should be only visible to any user only if the security policy explicitly allows it. So, for example, if let's say application A is not supposed to know anything about application B, it won't know about application B even through covert or like side channels. That's what it means by like not even indirectly, that it won't know about it in any way. So to prove this theorem, it was broken down into two parts. One was a abstract model and one was a C code implementation. So the good part about this paper is that the C code implementation, the abstract model was always formally verified, but the C code wasn't. This paper does exactly that, where even the C code has been formally verified. So we'll take a look at that. So first of all, like before proving this, the authors assume some things like the correctness of compiler, assembly code, hardware, and the boot code. They were correct. They were assumed to be completely correct, and all DMA access was disabled so that everything is routed through the kernel, right? Um, so let's see the proof of IFC. So the abstract proof was essentially created through creating ideas like how the flow policy will work, like who is allowed to send data to who, which partition is allowed to see what. Um, like as you can see, the non-leakage where no domain is allowed to s- get new data unless the policy allows. So some these steps were created and these were created into a model, and these were already essentially they were already checked through a formal checker. But the good part about this is the 8,000 plus lines of SEL4 code was also proven, like it was also proven for functional correctness in an earlier paper. But in this paper, they actually formally check it through a formal verifier. Um, so the final output of this verification was that the kernel prevents like storage channel leaks, wherein like you won't like there is no side channel if the kernel if any partition saves data to any place or like it reads or writes the data to any place, but the timing channels still remain unsecure. So as I have written, an example is that if a thread takes up more time than its time slice, it will essentially can be used as a covert channel wherein it is providing data to other partitions that hey, I am doing more task on this specific I am taking more time on this specific task, which can essentially give out some kind of information to the other partitions. um the This proof took a huge amount of time. It was like 21 months, which was essentially 51 person months, so that's like two people working for 21 months. Um, the reduced effort was specifically also due to uh, the earlier functional correctness proof that was done by the same team for SEL4. That took around 25% years. So that means that proving this model or this microkernel takes a huge amount of time. But like essentially the some real security bugs were also captured. So like for example, final capability bug. So what this bug um basically means is that if a kernel object is deleted, the object is only destroyed when the last capability for that kernel object is deleted. So this destruction, if it is seen by another domain, um, it can create some type of covert channel where a malicious app, if let's say, it could signal information by deleting the last capability to an object, and you can like the malicious channel can acquire data. Oh, this since it is still working, it is it takes up more time or something like that. Um, so. Like this verification, like it illustrates both like the strengths and limitations of SEL4. It does provide like storage channel protection, but there should be some type of mitigation for the timing channels as well. But like our personal final takeaways from this paper were that, well, in like real scenarios, as was assumed here, hardware and compiler cannot be fully trusted. There will always be some type of bugs or some types of differences, which can lead to like security bugs within through the kernel or through the hardware, and it cannot be always consistent. So that is like one drawback. Also, SEL4 is only usable for single core platforms. So like if in case we need a multi-core um, platform, SEL4 turns out to be useless because mm, there is no way for it to um, address coherency or consistency or things like that. So hence it is like only specific to single core platforms. Uh, Moreover, it also does not allow dynamic memory allocation. It is also to make sure that there is no, like to make sure everything is certain and there is no uncertainty, which can lead to security attacks. So yeah, SEL4 in general is a good, it turns out to be a good microkernel, but the efforts that are like the efforts do not actually, there is no return on investment for SEL4 since it takes up a lot of effort, but eventually it can only be used in very specific use cases. So I think yeah, that's that from our end. Please feel free to like uh throw us some questions over the Slack channel. Thank you.